Hey Arun, wish you a very good evening. Thank you for confirming that you can read my screen. Perfect. Just quick check, am I audible? Uh, okay, perfect. Good to know. Awesome. Glad you could join in, guys. How are you doing? Fresh week, fresh concepts, right? As usual, let's wait for people to join in. Once we have enough people joining in, we can begin our class. And a little bit of a heads up. So we are actually in the process of designing an advanced deep learning kind of course, right? Announcements, not really, Arun. I don't think I have any announcements today, but we are sort of preparing for an advanced course in deep learning where we are going to be discussing recent trends, right? Things like ChatGPT or things like DALI, where you essentially have representations for text and image both within your neural network. So those kinds of concepts, we are designing a course around that. So that will be starting after the NLP module ends. I see. Yeah. Oh, I see. Arun says, see some contests on my dashboard. So any news on that? Just clarification. Not from my end, Arun. I can definitely check if you have specific questions related to those competitions. You can let me know either here or on Slack, and I will take a look at it. So yeah, cool. Awesome. Perfect. So let's just wait for everyone to join in. So far in the NLP module, like we have been discussing mostly classical methods, right? We're slowly building our way to arriving at the turning point for NLP applications. The turning point was the introduction of transformers, where it finally became possible to use transfer learning to train other models or to generalize a certain architecture for multiple tasks. So that is kind of where we're headed. Today, what we're going to be discussing is again a sort of classical approach to topic modeling. So today we're broadly going to be discussing what are topics, what are documents, how to extract topics from documents, etc. Right? But we're not going to be using any sort of neural networks to do this. We're mainly going to be using statistics. So let's see how that's done. Of course, I'll wait for a couple of minutes before I start. In the meantime, I hope by now all the memes on this page are getting more meaningful, right? So the fact that we learned vectorization in the first class should be obvious in this meme here, right? Words get a vector, docs get a vector, everything gets a vector. Then you have word vectors, which eventually became word embeddings, right? And you know, so depending on the kind of optimization or penalization you apply, uh, your natural language generation can be penalized to just form short sentences. In fact, we saw a little bit of this last class, right? When we were talking about this predicting the next word. So we saw that by default, because of how probabilities work, large sentences are automatically penalized. So that was like a hidden penalty that we observed in our predictive modeling sort of thing. And yeah, and then you have the age-old meme: do a little text search, nobody bats an eye. Do a little NLP, and everybody loses their minds. Both are basically the same thing, right? So yeah, hopefully now the memes start making sense, like from a technical point of view at least. What do you guys think? Okay, fine. It does make sense to some people. I'm happy about that. Awesome. All right, guys. So we are 5 minutes into the lecture. We can now begin, right? Cool. So let's begin our discussion on topic modeling. Quick recap, just to sort of place where we are in the course and where we're headed, right? So the first few classes we spent on learning how to take a document, convert it to a vector. Specifically, we saw bag of words and TF-IDF, right? Then we took up words and we tried to convert those words to vectors using continuous bag of words and skipgram. Specifically in the last class, we tried to apply naive Bayes classification to predict what the next word should be given a prompt, right? We essentially saw how to perform language modeling. And related to each of these vectorization techniques, we saw certain examples. The examples mainly included how do you look for a document which is relevant, how do you look for documents which are similar, and stuff like that, right? So in the same uh, vein, right? What we're going to try and do today is basically how can we extract what a document is talking about, okay? And that is exactly what is uh, topic modeling, okay? So the agenda for today is as follows. First, we're going to be looking at something which is known as parts of speech tagging. The reason why we're going to be studying parts of speech tagging is because we want to understand if we can build some heuristic algorithm to extract what a document is talking about. So intuitively, if we are aware of what a noun is or what a pronoun is, what the subject of a sentence is, what the predicate of a sentence is, these things automatically come from the language, right? We have certain rules which tell us how to form a sentence in English. Can we sort of extract some meaningful information just by looking at the structure of the sentence? That is what we're going to try and do today. Based on the structure of the sentence, maybe we'll try to look for the most common nouns or the most common verbs, things like that. We're going to try and use to figure out what is it that a document is talking about. Okay. Once we exhaust our heuristic approach, we're going to try and study a statistical approach, which is essentially we're going to try and build a generative model. A generative model allows us to sort of imagine that the text which was generated or every document that we have generated comes from a random process. So we can assume that, okay, some random process is generating this. By studying that random process which is generating this document, we can talk about what were the different strategies this random process used to make this meaningful document, right? That allows us to actually get a very good hold of what topics are there in the generating process which gave rise to these documents. So intuitively speaking, we're going to try and do some sort of reverse engineering to see, okay, if a random guy was giving me this document, how would he have done it? Or how would that person have done it? And trying to reverse engineer what is the strategy used to generate this document, we're going to figure out what the topic is. Okay. Specifically, that approach is called latent Dirichlet allocation. So that is the method that we're going to be studying today. And the business case that we're going to be addressing is extracting topics of discussion from some sort of reviews that are there on Amazon, right? So let us go quickly and talk about the business case, right? Let's talk about the business case that we are going to study today. Okay, cool. So the situation is that you're a data scientist at Amazon. Okay, we're going to be tackling a very common type of problem, which is known as the insight discovery problem, right? You have a large amount of documents. You don't have enough people to sit and sort through those messages, right? You don't have anyone who is willing to put in the time or effort to sort through those messages. Can we sort of extract the essence of the content from that and present it with useful insights to whoever is involved, right? So for example, over here, specifically, we're going to look at music instruments. Okay, we're going to look at music instruments. So Amazon sells a lot of music instruments. A lot of people come and talk about whether the music instrument was good, whether it was effective for the job it was supposed to do. They provide reviews, right, for certain products. So let us say our job is to help the people making these products improve their products, right, based on the suggestions that are given in these reviews. Like that is the problem that we're going to address. So imagine, for example, we take a microphone, right? A microphone is a musical. It comes under musical instruments because, of course, voice is like I think the oldest instrument is our voice itself, right? When it comes to music generation, so something which is which allows us to capture different wavelengths or emphasize or de-emphasize certain things. You can imagine there's a microphone which is able to do that, right? So maybe someone who used that microphone felt, okay, this microphone is not able to catch the bass lengths well. If I'm performing to an audience, they are able to feel it, but this microphone is not able to convert it there. So that feedback, extracting those kinds of insights from these reviews is what we have to do. Okay. Everyone clear about the problem statement? I'll pause here. You guys can sort of take a look at this problem statement and then I will move on, right? So, okay. Hopefully now the problem statement is clear to everyone. We have to extract insights from reviews. Okay, cool. So now let us talk about what are the different ways we can actually send these insights to people, right? So the solution that you would send to your or present to these sellers could be a PPT, a word cloud, a list of topics, or a list of phrases or words being used, in the sense that you can just go, so you can make the problem very simple or you can make it very complicated, right? A simple version of this problem is when you are simply giving the producers of these instruments what are the most common words used. Okay, so that is like very simple for us to do, but it's not very useful for the people who are actually taking this or consuming this, right? Because the most frequently used words would probably not be able to uh, properly capture the intent of that message, right? Okay, so word cloud. Yes, Arun. So last class, guys, we learned word cloud. We saw how we can visualize what are the most frequent words using word cloud. So that could be the output that we give. But that is easy to do, difficult to understand, right? The opposite is also possible. We can do some sort of sentiment analysis and say, see, boss, these are the sentiments. The people who give you uh, fives are happy with it because of these reasons. The people who gave you threes are unhappy because of these reasons, and the people who gave you one are very unhappy because of these reasons, right? What is more important is, can we figure out what are those reasons? So essentially we want to look for certain keywords which will give insight to these producers to improve their product, right? And our job is now to figure out what are those keywords in this context. Okay, so it seems like a straightforward problem, but it probably isn't, right? And we're going to try and solve these problems using two approaches. The first one is parts of speech tagging, again, which is a kind of heuristic method, and the second is um, a statistical method, which is known as LDA. Okay, so let's begin. So, as usual, before we start discussing the actual approach that was implemented for this class, let us see if we can sort of build some intuition about how we can do this task if we did not know the topics of today's class, right? Let us say I did not tell you anything about parts of speech tagging, or I did not tell you anything about topic modeling. Imagine that you don't know this. What is it that we can do, right? What is it that we can do to solve the problem of topic modeling? Does anyone have any suggestions based on the techniques that we've already studied so far? I welcome any and every suggestion. You can just give me a few keywords. I will try and guess what your approach is, and we can discuss around that, right? So I'm going to pause here, and I want you guys to think, how do I get keywords which are important in the context, right? What are the different approaches? Have we done this before, by the way? When we were building vectors for documents, I think we did something like this. Do you guys remember? Okay, so what is the approach? What is the approach I can take? Yes, matrix factorization. Okay, perfect. Matrix factorization is a method that we used. Okay, cool. Which matrix did we use, Indradeep, over there? So we can build matrices in multiple ways, right? We can, so see, let us first try and understand what all we have with us, okay? So first of all, we have this large set of documents, okay? We have this large set of documents which we call the corpus. And then we have these individual documents, document 1, document 2, all the way up till document N. Now, each of these documents have sentences, right? Sentence 1, sentence 2, sentence 3. For this document, then this document has sentence 1, sentence 2, sentence 3, so on, right? And if I extract all the unique words that are there in this corpus, right? What is that called? All the unique words in the corpus. What is the technical term for that? Vocabulary, right? So I can extract all unique words to build a vocabulary. Okay. So now in this context, guys, with this notation, right? With this notation, can you explain to me what is the matrix I have to factorize and why? Okay. First, tell me the matrix. In fact, I think we have already discussed two important matrices, right? We've discussed two important matrices. So can you guys give me an idea of how I should build the matrix first of all? What should be the rows? What should be the columns? Anyone? Okay, documents in rows. So let us say I have n documents. So I will have a matrix now. For matrix factorization, what I'm going to do is I'm going to first put my documents in my rows. So the number of rows is n over here. Okay. What should be the columns? Vocab as columns. Okay. So V, right? Let me say the vocabulary size is V. Okay. Let's assume that size of vocabulary. Okay. Okay. So I have n cross V. Okay. Now, if I take this matrix, which is basically telling me in a document, what are the words that I have, right? This is like a bag of words matrix. Okay. This is a bag of words matrix. If I take this matrix and I factorize it into two parts, let me say A, B. Okay. Typically, when we factorize, we have the freedom to choose what the K should be, right? So now let me assume that I'm taking this bag of words sort of model. I'm factorizing it into n cross k followed by k cross v, right? So I'm writing this matrix as a product of these matrices, and now I have these two things. Right? Okay. So if you guys remember our discussion a few classes back, this is essentially a word embedding. Okay, is it okay if I look at this n cross k matrix, right? So if you look at this matrix, this is essentially taking n documents and it's creating row vectors, right? K is the number of columns. So if I take a row vector, the length of that row vector is going to be K. Okay. This over here is an embedding for what? Is it an embedding for my documents or is it an embedding for my words? What do you guys think? The row vectors, are they embeddings for words or are they embeddings for documents? Docs, obviously, right? And similarly, this is going to be embedding for words. Okay, right? Cool. So between these two matrices, where do you think that important words for a document is? Should I look over here in this matrix or should I look in this matrix? What do you guys think? Does it make sense to look at the doc embedding or the word embedding? It kind of makes sense to do it. Okay, so Indradeep's guess is A because it is essentially giving him a vector which goes to documents. But Indradeep, if you think about it, right, I actually agree with Arun's suggestion. Okay, yeah. So Arun's suggestion is what I will go for. Arun basically says that we should be looking at the embeddings of the words, right? Why embedding of words? Because the important words for this entire corpus, remember, we're dealing with a corpus, not just individual documents. We have some assumption that this corpus has related documents inside it. So now, if I go inside this B matrix and I hunt for embeddings of words, don't you think important words will show up in this embeddings over here? So if it was me, I would try and look at this one, right? I would try and look at these embeddings to sort of see what are the most uh, commonly occurring or what are the most important words in this vector space. And yes, in private chat, a couple of guys are asking me, is this a naive approach? Yes, this is a naive approach. Okay. This is an approach where we are trying to guess how to do this stuff without using any of the things that we're actually going to study today. The reason why we're doing this, guys, is because these concepts, right, are what we're eventually going to use to build our architectures. When we come to deep learning, these kinds of discussions is what will help us try and understand how did the guys who built these architectures actually think about the problem. Okay, so the main reason why I spend a lot of time discussing naive approaches is because we want to understand where those guys are coming from who design these architectures, right? Matrix factorization approach is kind of good. Why is it good? Because if we understand this, right, we will see how this connects to the topic modeling today. Okay, so just a little bit of heads up. If you are able to follow this discussion, it will be easier for you to understand topic modeling. Okay, cool. Coming back to this. Okay, so I have one naive technique. Okay. I have one naive technique now, which can essentially help me topic model, right? I can basically look at this embedding vector. I can look at what are the important words over here. Those words is what I will call a topic. Okay. Those words is what I will call a topic. Now I will go back to this embedding docs dictionary and I will see which word is important for which document, right? See, first understand this is a two-step process. I will first understand what are the important topics or what are the important words inside these documents which were keep occurring over and over, right? If they keep occurring over and over, they're probably important, right? So the word convolutional neural network is definitely going to appear a lot of times in a CNN paper, right? That is what I'm talking about. So first I will go and I will figure out what are the words that are important in my corpus. Once I have the important words in my corpus, I can backtrack and say, okay, out of these 100 words, this document talks about 3 of these words. This document talks about 5 of those words, something like that, right? That is essentially how I'm building a topic for a document. Okay, cool. So now that we've understood this, can you guys think of anything else that we can apply here? Maybe something to do with, like I just want the name of a naive approach for this that we've already studied, guys. Yeah, exactly. Kind of clustering. We are trying to cluster. At the end of the day, Indradeep, topic modeling is like clustering, right? Think of it this way. If I first go and I put this vocabulary, if I put this vocabulary in a certain space, right? If I start clustering words which appear frequently together, don't you think the most important word in that cluster is nothing but the topic of this cluster, right? So, okay, let's kind of visualize that. Okay, let's kind of visualize this process. Topic modeling as clustering. Let's visualize this. Topic modeling. I really like this suggestion. By the way, guys, before I was looking for TF-IDF, okay? TF-IDF is something which tells you how important a word is with respect to the corpus rather than just a document. Okay? So I was really hoping someone would have said, can't we just apply TF-IDF here? That is one of the naive answers I was expecting. So in an interview, it sort of shows that you understand what TF-IDF is and how it comes about, right? So one extremely naive way of doing this is just do TF-IDF, select all the words which have high TF-IDF ratings because those are words which are not only important for a document, but are important from the corpus level as well. Okay, so that is what I was kind of expecting. Let's forget that. Now I have a much better suggestion. Let's sort of try and visualize what clustering would look like here, right? This visualization will again help us understand LDA better, which is why I'm going to spend some time on this. Okay. So now let us say I have these documents, right? Let's say I have these documents. I have this. Let me take this setup over there. Okay. I have all of these documents, right? Let us say I first take all these documents, put them together, and simply build a point cloud of different words. Okay. Let us say I do something like word2vec and I try to build a point cloud of words. Now, in this kind of a cluster, right, where words which occur together are closer, words which do not occur together are farther apart. Are you guys able to imagine such a point cloud? We have seen something like this when we imagined word2vec, right? Guys, we saw that point cloud. We had that visualization. So I want you now to imagine that point cloud which we saw in word2vec. I'm going to basically apply word2vec on this entire corpus. I'm going to convert all words into vectors and I'm going to plot that point cloud. Don't you guys intuitively feel that words which appear together in this, like let us say these guys over here, right? Let us say these points over here are related to convolutional neural networks, right? Let us say these words over here are related to, let us say some words over here are related to GANs, right? Which occur a lot in GAN papers. Then you have these words over here. Let us assume this one. Let's take a good color, right, for this. Where is this one, right? I have one kind of cluster over here, which sort of brings me to say variational autoencoders. right? So yeah, diffusion. Yeah, we can have diffusion also as one of the keywords. Thanks for that. Cool. So we have diffusion somewhere here, right? So we can now try and understand this problem of topic modeling as taking these different clusters of words which appear close together and figuring out what is that one or two words which define this cluster. Okay. Within this cluster, what are the important words? That is what we're after, right? That is what we're after. Okay. Naively speaking, the words that we should select as the topic, do you guys feel it should be nouns, pronouns, verbs, adjectives? Which of these do you think? Everything that I've written here, for example, is it a noun? Is it a pronoun? Is it an adjective? Is it an adverb? Nouns, right? Okay, awesome. So, intuitively speaking, if I go to these clusters and I try to understand which words have appeared the most in what context, right? And I say, okay, this one word, variational autoencoder, has appeared as a noun a lot in this cluster. Then can I go back and say, okay, the topic that this cluster is representing is variational autoencoders. The topic for this cluster is CNNs. So this is how I can basically extract the topic words, right? That is how I can extract the topic words. So it is completely fair to understand topic modeling as a clustering problem. Okay. Okay. Now that we have understood and we've talked about two really good naive approaches, right? Topic modeling and matrix factorization and clustering. Let us see if we can put it together to do something way smarter. And that is what we're going to try and do in today's class. Okay. We're going to try and do that in today's class. Okay. So let's go back. So the first thing that we're going to try and understand is this thing called parts of speech tagging. Okay, we're going to try and understand parts of speech tagging first, and we're going to understand this with an example. Okay, so in deep blue over here, I have given you a sentence, right? He used a convex optimization algorithm. This is my sentence. What is parts of speech tagging? Parts of speech tagging is simply getting this word. Okay, so all words over here in this particular sentence have a certain role to play. Okay, generally when we talk about language, there is always some structure, right? There are some well-defined rules, right? Unless you're Yoda, this is the correct sentence. Okay, if you're Yoda, you would probably switch the subject and predicate and you would say something, right? So as far as English goes for people like us, uh, the rules that are there for sentence formation are pretty well defined. Okay. For example, before a verb, you should have a noun or a pronoun. This one rule we all know, right? It doesn't make sense to first talk about a verb and then bring in the person or the noun with which this verb is associated, right? Of course, there are edge cases, but most of the time, a verb has to be associated with a pronoun or something like that. Then you have these nouns, which are the main subject which we're talking about, right? Then you have these words which are basically describing something. So, for example, convex optimization as a whole is describing this word algorithm over here, which is a noun, right? So every word in this sentence, okay, plays a certain role. Can you guys tell me, based on your understanding of the English language, right? Do words always play the same role or can the role change? Can a noun become a verb sometime? Oh, no. Really? Can a noun become a verb? It can, right, guys? Come on. English language is weird, right? Yeah, English language is weird. Basically, you can take a word, you can use it as an adjective also, you can use it as a noun also, you can use it as a verb also in some cases, right? So, okay, that's an extreme example, but there is this recording of Osho who discusses the multiple uses of this word. It's a swear word, so I don't want to say it, but I don't know if you guys have come across it. But maybe you can Google Osho talking about a certain swear word which occurs in multiple contexts, right? So you have these. Okay, nice. Mayur knows about this. So essentially, different words in a sentence can play different roles. Okay, and basically why? Yeah. So in private chat, some people have told me what the swear word is. Okay, let's not talk about it. Oh, nice. Mayur says Osho is from his town. Perfect. Okay, so The reason why I'm discussing this, right, guys, is because parts of speech tagging is not a well-defined problem. Okay. If I take a word, I cannot tell you beforehand what this word is going to be. It depends on the context of a sentence, what that word is going to be, right? So whenever we are doing a complicated task like parts of speech tagging, we have to build some sort of predictive algorithm in the sense that we have to build an algorithm which is random. It may not always give you the correct answers. And in fact, the same sentence can be visualized as different in different settings, right? So it's not a well-defined problem. Typically, an algorithm which is able to take one sentence and tell you what the meaning or what the role that word is playing in the sentence, that kind of algorithm is generally based on a statistical model. Okay. So the kinds of algorithms which I know of is something based on hidden Markov models. So the class of algorithms which can sort of, yeah, the class of algorithms which can sort of do this for you, right? Take a sentence, tell me what is the part of speech. That is going to be random. And the class of algorithms is known as hidden Markov models for this. Okay. So how this hidden Markov model works is it will take a large supervised data set where some people have already told this hidden Markov model uh, what the part of speech is for a certain word. Then this model will automatically learn how to predict whether given that the current word is a verb, the next one should be one of three. Okay. So then it uses one of those three with some probability to determine what the next word is, right? So it's a probabilistic model. Okay. So what we're going to do is we're not going to discuss in detail how this works. Rather, we're going to sort of take Spacey, which is a very, very nice library, which does this automatically for you. And we're going to try and understand how to get that to work. Okay. So let's go ahead and do that now. Let's go ahead and see how to use Spacey to do parts of speech tagging. Okay. Cool. So the data set that we're going to work for is available here. So all I'm doing here is downloading it. Let us visualize what this data set looks like, right? Okay. Quick reminder to everyone, we are working with musical instrument reviews. Okay, that is the case study for today. The data set that we have in our hand is basically different reviewers. Okay, the reviewers are identified by this reviewer ID. There is this identification number. I guess it is to identify which review is associated with this reviewer, right? This gives us a reviewer name. This essentially gives us the rating, right? If you remember on Amazon website, you can actually tell Amazon whether the review was helpful for you or not. So this column is tracking how many people found it helpful, something like that. Then we have this reviewer text, right? This is the text that we actually have to analyze, okay, for topic modeling, okay? And this is the rating that the person has given for the product. This is the summary that the person has given. Okay. In Amazon, you have to give a summary also. You have to give the text also. So this is the summary part of that. This is the review time. So I guess this is the time at which the review happened, right? So this is in Unix form. What do I mean by Unix form? It is the timestamp. So this is not understandable by us. This is only understandable by machines. We need something like p.2 date time to sort of convert it to a proper date time format. Okay. So this review time that you see here is nothing but you take this, you convert it to a readable format, and you're getting this. Okay. So specifically, this review happened on 28th February 2014. Okay. So this is what our data looks like. Okay. Of course. Yeah. So the date format looks weird. This is what we did to fix the date time, right? We said pd.to date time. We converted that to understandable dates, and we got that. Let us first now see what the distribution looks like, okay, for our data. So it looks like most of our data is between 2005 to 2014, okay? Not most, all of our data is pre-2015 over here, but most of our data seems to be from 2013-14, right? So this is where most of the reviews are from, and we have kind of few reviews over here, maybe because these are the years when Amazon did not have so many musical products. And as the years went by, more and more people came in and started selling musical products on this website, right? So maybe that could be one reason why it looks like this. Moving on. this is what the ratings look like. Okay. I don't know why this has happened, but there's a slight shift over here. The bar that you see here is actually for 3. This is 4. And the bar that you see here is actually for 5. Okay. So it looks like most of the ratings on these on the website are positive, right? Largely positive reviews. So generally, when people don't like a product, they don't even bother, right? Or it could also be that if they dislike a product too much, then they will go and give a negative review, right? So this could be one explanation for why this distribution looks like this. But essentially, this is how the ratings look like. Okay. Now, we're not really concerned about the sentiment or ratings, right? More than that, we want to sort of tell the uh, seller what is it that you can improve in your product to make it better for others, right? That is the kind of suggestions we want to give, which is why we're going to apply topic modeling ideas to this to solve this problem. All right. Okay. So first things first, we're going to try and exhaust all the simple ways of solving this problem. We're just going to go and check all the frequencies. We're going to build a this thing word cloud plot, and we're going to see, right? So first, let's get rid of the simple techniques and see what we get. Okay, cool. So from collections, I'm importing this counter. So collections is this Python package which has a lot of helpful data structures. From there, we can get this counter, which will essentially just count or sort of get the this thing list of okay, here at least I'm just getting a flattened list. I guess I'm going to be using the counter later on to sort of build that frequency dictionary, right? Okay, moving on, we're going to pip install NLTK and word cloud. As I said, we need word cloud. NLTK is obvious, it is useful in a lot of places, so we're going to install both of these. And yeah, once that's done, let's move on. Okay. So we have this one function here, which is essentially going to just do the word count plot. And we have this tokenizer over here. So we're going to use this word tokenize from nltk.tokenize, right? That is what we're using over here. Okay, cool. And counter all is basically using this counter to count all the occurrences of these flattened words, right? Okay. So these are, this is nothing but some basic code to set the whole process up. Once we've set the whole process up, we can see, right? Okay. So first, let us see what are the most frequently occurring characters here. Can you guys tell me, does this give us any insight when we run this? We don't really get any insights. The words that we've picked up or the characters, the tokens we've picked up is very useless. That their punctuation marks, I and the all that, right? Yeah, stop words. So we have to first remove all the stop words. But just for completeness, let us see how the word cloud also looks like, right? See, the word cloud and the frequency are very related. Okay. So since dot has a very high representation, we see this huge dot over here, and we see this huge comma over here, right? Then we see this huge I, and all of these things, right? We see all of these things over here, but this is not very useful. So we will use nltk.corpus's stopwords to remove the corpus, right? Yeah. So in private chat, someone is telling me, why do we always forget to do pre-processing? It's okay. It's like we do these things just to discover the importance of it, right? So that's all. Okay, cool. Moving on, we have from nltk.corpus import stopwords. We're going to remove these stopwords from all our reviews, and then we're going to do this, right? So now I have this new function called tokenize clean, which is going to do word tokenize if and only if W is not in English stopwords. Okay. So if it is not in English stopwords, then only I'm going to keep it. And I'm also going to say W dot is alpha. Do you guys remember this Python function is alpha? The string function. This is a Python string function, right? Okay, if you don't remember, let me tell you. This will basically give you true if the string contains alphanumeric characters, and if it contains something like a full stop or a exclamation mark or something, it will return false. It's a binary function, right? It will return, it's a true false function. It will basically return true if it only contains alphanumeric characters. Yes. Oh, is alpha is only for alphabet? Let's check that, right? Okay. How do we check that? Let's open a terminal real quick. Let's go to Python. Say A is equal to hello. Say B is equal to say high 1 3, right? Let's say A dot is alpha is true. Let's see B dot is alpha. Okay. So is alnum. Okay. Arun says is alnum is the one we use for alphanumeric. Okay, fair enough. So what we're using right now is the is alpha function, which only checks for alphabets because maybe we don't want to keep alphanumerics, right? Alphanumerics could be something like ID or something. So if we look at our data set, maybe these IDs or something should be alphanumerics, right? So we don't want to keep stuff like that. Yeah, R2D2 we don't want to keep, although it is a proper noun. Yeah, although it is a proper noun, I suppose R2D2 won't appear. But yeah, unfortunately, we're going to remove R2D2 from this. So okay. And if you think about it, Elon Musk's child's name will also not pass this test, right? So maybe he named his child smartly to sort of make sure they're not indexable in most of these this thing. So yeah, okay. Sean says we're not dealing with Star Wars corpus. Fair enough. Okay, all right. But just to be clear, we now have this tokenized clean function, which is only going to keep words which are not stop words and which are alphabetical. It is going to get rid of any strings which contain anything other than an alphabet. Okay, so that is the criteria we've put. Moving on. Now, if we do the same thing, right? Moving on. Now, if we're going to apply the counter function, get the most frequent words. The words that we get are guitar, one, great, like, use, good, sound, strings, well, get, right? Now it sort of it has started seeming like this thing. It seems like we're now getting topics over here, right? It now seems like we're getting topics here. So essentially, we are now moving on to a place where we get important words here, like, right? So since we are dealing with musical instruments, it's nice to see that the word guitar appears in a lot of places. It basically tells us that most of the products which are there in our corpus are guitars, right? Okay, or guitar related. It could also be guitar straps, guitar strings, stuff like that. But most of the words in our corpuses are guitar related. You have great, one, like, use, sound, strings, all these words, right? But again, these are great for understanding what our corpus contains, but it does not really give us any insights about each of those, right? So it's good to see this, but we're not done yet. We still don't have an idea of what the topics are. So of course, now that we have understood what are the most commonly used words, it is important for us to go ahead and see how what is being talked about these words, right? So what is it about the guitar that is good? What is it about the guitar that can be improved? Or what is it about the guitar related product that can be changed? That is the insights that we want. So we're not done here yet. So let's move on. So, like I said, the library that we're going to be using today to do this is Spacey. Gensim is something we're going to use for the next part, but I have just installed both of them here. Okay, so this basically completes the installation, and now we have to sort of see what are useful, what are not useful, and things like that. Okay, cool. So before I go ahead with this, right? Before I go ahead with this, I sort of just want to take you to the Spacey documentation, and I want to give you an idea about a couple of things. Okay. So let's quickly go to Spacey's documentation, the main library architecture, and let us understand what is it that Spacey does when we give it a certain text. Okay. It's important to understand this to use the tool effectively. Okay. So broadly speaking, guys, what Spacey does when you give it text is it automatically does a lot of pre-processing for you. Okay. That is what's nice about Spacey. Spacey already understands that if you're using Spacey, you're going to do something related to parts of speech tagging, or you're going to do something related to tokenization and stuff like that, right? So it has built this very nice architecture around those frequently used tasks that you usually do with text. Okay. So once you get text, broadly speaking, you encode this text in something which is known as a language class. Okay. This language class basically gives you an object. That object is now what you can apply different tasks on, So we have this language. So the language is generally one of these. Okay. So you have these languages such as English, EN Core, Web SM. So guys, over here, the SM stands for small. Okay. EN Core Web SM. Then we have EN Core Web MD. The MD over here is medium. Then we have EN Core Web LG. LG is large. And EN Core Web TRF. I'm not entirely sure, but I guess this is larger than large, right? It's slightly larger than large. So these are essentially different language models that it has. Each of these language models are a collection of a few very frequently used tasks. Okay, let's understand what those tasks are. So English pipeline optimized for CPU. So this EN Core WebSM language, right? This is a class, guys. Remember, this is a language class. This class contains the following components. It has toke to vec. So it's a tokenizer to vector representation. It has a tagger. It has a parser. So this tagger is, it has a parser. It has a center. So this is like sentence level operation. Then you have NER, which is named entity recognition. You have attribute ruler and lemmatizer. Out of these, this tagger is what we call parts of speech tagging, right? This is the tagger. So specifically, we are interested in the output of this component from this language. Okay, cool. So how Spacey generally works is you take text, you give it to this language model, it will automatically pass this text through all of these processes. Okay, it will pass it through all of these processes, and it will be ready for you to visualize once it finishes converting everything to the required format. Okay, so the architecture is a bit like this. Once you have a language, once you pass this text to a language, it automatically builds a vocabulary set called the vocab class. This vocab class essentially creates the lexeme. So if you remember, lexeme is nothing but the smallest part of a word which holds some meaning, right? So that is what the lexeme is. Then you have these language which contains these different components, right? It contains a tokenizer, it contains a pipeline, and these eventually bring these whole language things together in the form of a graph, where where the words are nodes and the occurrences are basically the edges, to create something which is known as a document object. Now this document object will have a tokenizer and a lot of other things. So broadly speaking, whenever you give a certain text to this Spacey, it will apply this language on that text and it will automatically create all of these things. Okay. So now let's see this in action. Let's see this in action. Okay. So for this example, I'm going to be using this EN Core Web SM. Okay. So now to give you some idea about what is the difference between SM, MD, LG, right? The basic difference is to create these parts of, so out of all of these, right? Out of all of these tasks that we do, some of the tasks require training. Okay. So like I said, a parts of speech tagger is a hidden Markov model which requires some training, right? This SM basically tells you what is the size of the data set which was used to train this. Okay. So for example, the size of this EN Core Web SM is 12 MB. Okay. It used something like a small data set to train all the components over here. And that is where the size of this is 12 MB. Now a slightly larger data set was used to train the MD, and the MD size is 40 MB. Okay. Even larger database was used to train the large model. So this is 560. And then and this is some sort of optimized. So I'm not sure what this TRF means over here, but my understanding is that this is some sort of optimized kind of data set which was used to do this, right? So I guess this will become clear if we sort of go through these sources for what kind of optimization they did, but I'll leave that for later. For now, what I want you to understand is each of these things that I have over here, each of these trained pipelines are already available for me. Out of them, I'm getting this EN Core Web SM. Okay, this is the trained pipeline that I'm going to use from Spacey. Okay, cool. So once I have gotten that, right, the first thing that I have to do in Spacey is I have to create an object of this class. So I have to actually say spacey.load EN Core Web SM. Then it will create an object of this language class. Oh, I see. So guys, Anil has found the answer for TRF. TRF is a transformer model. Beautiful. Thank you so much, Anil. Okay. So in private chat, Anil has let me know that TRF over here basically stands for transformer. So this was essentially, so my assumption now is that each of these things over here is a transformer. Whatever used to be HMM or something somewhere else is now a transformer which is being used over here. So I guess this will outperform most of the above models. But for this example, since timing and size is a limitation, we are going to be using this WebSM, right? Okay, cool. So what I have to do now is I have to load this model and create an object out of it. So this NLP over here now is an object of the class, this language. It's an object of this class language, which is over here. Okay, object of this class. If you notice, NLP is like the convention. So let me zoom in a little bit. So by convention, we call this object NLP. Okay. So a lot of spacey code, you'll probably see this. Now what we're going to do is we're going to take a review sample. We're just going to take the first one. Okay. The first review which was given. Let's read it. Not much to write about here, but it does exactly what it is supposed to. Filters out the pop sounds. Now my recordings are much more crisp. It is one of the lowest prices pop filters on Amazon, so might as well buy it. They honestly work the same despite the pricing. Okay. So the musical component that they're referring to here is this pop sound filter. Okay. Pop filter is the name. So if you guys are wondering what this is, guys, have you seen these recording studios? Have you seen this setup where there's a mic and there is this like, what do you say? There is like this disc with a sheet of cloth, right? There's like this piece of cloth around this disc, which is there, mesh. There is this mesh which is there in front of that mic, right? So that is a pop filter. So usually when you're recording, right? Whenever we put some sort of emphasis on certain syllables, so like pop I'm basically putting emphasis on P, right? So that will actually create a very large signal and it's kind of disturbing to listen to. So this pop filter sort of takes care of that. It removes that extra emphasis that you put on syllables and it kind of makes it easier to listen to. Okay. So that is the musical thing that they're talking about here. So if I now had to extract the topic over here, do you guys agree or disagree that pop filter should be a topic that I get out of this? Agree or disagree? Is this one way for me to check whether what I'm doing is correct? Right? Okay. So now whatever method I use for this one, I have to now somehow get pop filter out of it. I have to also get good or something like that, right? So another keyword that I could probably get out of this is the sentiment associated with it, which is good, right? So that's the idea here. Okay. Moving on. Now when I actually pass this review sample, right? This review sample is basically this string over here. I pass it through this NLP class. I'm basically giving it as input to this. I get the spacey process review. Okay. It looks like it is unchanged, but if you notice carefully, this is now an object of spacey.tokens.doc.doc. Okay. So now this has been converted into an object of this class of the doc. Okay. So it has applied all these pipelines to it and it has converted to an object of this doc class. And that is what we're working with now. Okay. So I now have this object of type doc, and from C process view a single token out of this doc, right? So this the zeroth doc over here is this word not. Okay, it is also the first word which comes here, right? So in a string, if I had given this 0, I would just get this letter N. But now from this object, when I give 0 to it, I'm getting the whole word over here. The whole token is what I'm getting. Okay, and the type of this object is token. Okay, just wanted you to notice that. Now if you now want to get what is the part of speech associated with this word, right? If you now want to get that, you have to do dot pos underscore. Okay. So spacey has already applied parts of speech stacking on the sentence. It has already stored the result over here in this. Oh wow, what's yeah. So it has already stored the. It has already stored the thing over here. So parts of speech, yeah. So this is basically a this is basically a variable of this token class. Okay. So it's already stored it there. And the way we get it is this part. So now the word not is essentially now of type part. Okay. What does this part mean? Let us see. Okay. Let's see. Now, one moment. Let me just quickly get that. There is documentation which tells us what each parts of speech tag list is. Let me just quickly get that over here. Yeah. So there is a table which basically tells us what this is. Let me get that over here. Right. Okay. So part should come somewhere here, right? Part. So part basically means particle, right? Is not all these kinds of things are particles. So this is what it is telling us, which is kind of correct, right? Okay. So now we know that. So now if we want to basically see what is the parts of speech tag associated with each word in our document, which is over here. This is our document right now. To see that, we have to basically access this pos variable. Okay. So I can write some very simple logic to just check if something is a noun and just keep the nouns, right? We just talked about this a while back. The topic should be nouns. It's highly likely that the topic of our cluster or this thing has to be a noun. So let us go ahead and see if let us do some simple processing to only keep the nouns in this. Okay, only keep the nouns in this. So there are two separate tags in Spacie for nouns. Okay, I see. That is what happened. Okay. So there are two separate things for nouns. You have proper nouns and you have nouns. Okay. So Spacie actually differentiates between proper nouns and nouns. So if the detected word is either noun or proper noun, we're going to keep it. Otherwise, we're not going to keep it. Okay. So now let us see. So now I have the word pop, which appears as a noun, the word sounds, which appears as a noun, recordings, which appears as a noun, prices, filters, Amazon pricing, all of these are nouns over here, right? Okay. Here's a problem. Pop filters is what I was expecting as a noun, but this pop is only pop is coming separately as a noun and filters is coming separately as a noun, right? This is obviously a problem. So we have to fix this problem. Like essentially we want to make sure it is putting these things together, right? Yeah, something like a bigram, exactly, right, Arun? So if we had somehow accounted for bigrams being present here, that is one way we could have dealt with the problem. But actually there is a nicer way to deal with the problem using the rules of grammar. Okay, using the rules of grammar it's possible to come to a solution. Let's see that now. Okay, cool. So the process of using rules of grammar to club these commonly occurring words together is called constituency parsing. Okay, constituency parsing. What do I mean by this? Okay, so we can basically build a hierarchy over here, right? We can say that if two nouns appear one after the other, isn't it highly likely that both of them are together a single noun? Like if I have two words which are both nouns in that context, right? And they're appearing side by side, isn't it highly likely that the two words combined together is also a noun, right? I can make use of these kinds of rules to build something which is known as a constituent graph. Okay, so if we were writing this code on our own, we would have to use something like a context-free grammar or a finite automaton to implement this. Okay, so those of you who are from a computer science background, you are already familiar with what these are. For those of you who don't know what this is, guys, in this topic in computer science called uh, this thing, this, yeah, formal languages is correct, but the name of the topic is automata theory, right? Yeah, automata theory, but it's also called theory of computation. Yes, yeah, theory of computation and compiler design. Like in these two topics, right, we basically study a lot of ways for us to build compilers. So this kind of technology is what is used to build your compiler. So I'll give you a very simple example. Even if you don't know all this, if it's sounding scary, don't worry. Think about a simple if-else condition, right? We always know that after an if, whatever is going to come is a condition which should evaluate to true and false, right? That is what we know. So the or the people who wrote the Python language, they basically defined that you look for this word if, whatever comes after it is now going to be a condition, and based on that condition you are going to execute a certain block, right? So if you think about it, the tree that we will draw over there for a simple if else condition will look something like this, right? Sorry, the tree that will appear for an if else condition. So I will have this if, and then I'll have this, right? Okay. So what a compiler will do is it will take this token, it will put it as a node. Okay, it will put it as a node. It will take this condition, it will put it as a node. Okay, it makes it a node, and together it will create a new parent node now, which is called the if else block, right? So the whatever code we write to do these kinds of things is exactly what we will do over here to essentially say that if I have a noun NP, right, which is a noun. So if I have a noun, or I have a pronoun, or I have an adjective followed by an adaptation followed by a noun or a pronoun, this rule basically tells me if you have multiple nouns together, okay, then you should group them together as a single NP. Now NP over here is noun phrase, okay? NP over here is noun phrase. So now what this program is going to go and do is, if it detects a noun or a pronoun or an adjective along with all this, it's going to club them together into something which is known as a noun phrase. Okay. So if you don't want to worry about how to implement this, don't worry. Spacy does this for us automatically. Okay. It automatically does this. It has defined its own rules for defining these noun phrases. And we're going to take advantage of that to do topic modeling over here. Okay. So let's go ahead and see how to do that. So okay, and there is actually one caveat over here. Okay, one caveat in the noun phrase rules that Spacy defines. It also takes pronouns over there. Okay, so it takes nouns as well as pronouns in the noun phrase. So before we use Spacy's way of doing noun phrases, we have to do a little bit of pre-processing. So let's understand this. So Spacy treats pronouns as nouns as well. Okay, so when it is extracting noun phrases, it will put pronouns also there. Pronouns are basically like he, me, she, it, they, things like these are pronouns. If you're familiar with gender fluid movement, you have to now understand that people have their preference of pronouns. So it's kind of important to know this if you want to be, what do you say, politically correct. Yeah. So but essentially that is not going to help us here for this kind of a task, right? So now what we're going to do is we're going to go and we're going to see how to extract these noun phrases first. So to extract these noun phrases, what we have to do is we have to access this thing which is known as noun chunks. So noun chunks is basically a variable which is going to store all the noun chunks that this encountered when it was parsing the sentence, right? So what I'm going to do to get all the noun chunks over here is for C in spacy.processReview.noun chunks, print all the noun chunks. Okay. So see what output we get. So we have here it, which comes as a pronoun. You have exactly what, which comes as an adverb followed by a pronoun. Then we have it, which is a pronoun. The pop sounds, which is the pop sounds, which is a determinant followed by a noun followed by another noun. Then you have my recordings, which is a pronoun and noun. Okay. So you have filters over here, which is a noun, right? So broadly speaking, this is able to do what we want. Okay. The only caveat over here is these pronouns are kind of appearing here, which is making this weird. So now what we're going to do is we're going to keep things in this parts of splash tag. So now we're only going to print out those noun chunks which have a noun and a prop, which are a noun and proper noun. Okay. So for example, now we have pop sounds, then we have recordings, then we have prices, then we have filters, then we have Amazon followed by pricing, right? So now by doing this to Spacy's output of noun chunks, we're able to get a kind of reasonable list of topics over here, right? So it tells us that this document is talking about pop sounds, it's talking about recordings, prices, filters, Amazon pricing. So we can say that this review talks about pop sounds, it talks about prices, it talks about a filter. So the filter is probably for this pop sound. So let us say I just do this for every document which is there in my corpus. Do you guys agree or disagree that this is a reasonable set of topics? Is this reasonable? By looking at just these words, can I guess that what is this review talking about? I can do that, right? Okay, perfect. So this becomes a very nice way for me to extract topics using a heuristic process. We basically applied our knowledge of English grammar rules, parts of speech, and stuff like that to extract what could be the most important words for describing this corpus. Okay, that is what we have achieved here. Okay, so now if we now go ahead and do this for our entire thing, right? Uh, it kind of gives us the following result. Okay, so we can go and we can essentially get a few topics for each of our documents, and they look like this, and we can try and guess key what that review is kind of telling us. Okay, cool. So we go ahead and apply it. It took about 4 minutes and 36 seconds for it to work through this entire document, right? So I'm not going to rerun this. It's going to take too long, but essentially the result is available for you here, right? Okay. But now here is a problem that I have with this this approach. Okay, the problem that I have with this approach is fine. It's telling me what the topic is. It's not telling me something useful about the topic, right? I still don't have insights. I still have to. So if I give this as an output to whoever has asked me for topic modeling, they will say, "Boss, it's great and all, but we don't know." Without looking at the review itself, we don't know what the improvement suggestion is, right? So that part is still left. So now we have to go and figure out, is there a way for us to use any heuristics which tells us the relationship between these topic words and the other words which are there in this review? Okay, so that part is left now. We don't know if we're talking about pop sounds. We don't know if this review is telling that this we don't know if the review is telling us that it eliminates pop sound successfully or it does not eliminate pop sound successfully. That is what we were mostly interested in, right? So this is great for a first level answer, but this is not perfect. So let's go and see what else we can do. Okay, so the next thing we can do is we can essentially look for words that they're related to. Okay, and this kind of parsing, heuristics in heuristics language, this kind of parsing is known as dependency parsing. Okay, so in dependency parsing, what we do is we basically we try to build a tree now. Okay, we try to build a tree where each sentence along with the parts of speech also tell you how these different words or parts of speech are related to each other. Okay, so let's understand this through an example. Okay, so we have this text over here. We all love learning at Scalar Academy. So over here, below these words, right, below these individual words which are there over here, we have pronouns, determinants, verbs. ADP is adverb. Oh, no. One moment. Let's go and see what ADP is. Add position. Okay, it's an add position. And then we have this proper noun, right? Scalar Academy. So we have these individual things over here, but these things that you see above here, right? AP pos, nsubj, xcomp, prep, pobj, these are essentially descriptors which tell you how are these parts of speech related to each other. For example, let's look at this verb love. Okay, verb love has a relationship with this verb called learning as xcomp. So let me just quickly get that also. One moment. Dependency spacey. I just need to understand what this means. So just give me 1 second. Tags. Let's see if I can find a. Yeah, cool. Got it. So these are giving me that, but it's not. It's not giving me the scheme, right? Right. Just give me 1 moment. So this is the morphology. Okay, I'm not able to find a readily available table for this. I thought I had one, but this. Oh yeah, it does give me. Okay. This is it. Just 1 moment, guys. I'll just put it over here on the screen. Okay, cool. So the Spacey documentation has this table which explains what each thing is. I'll have to reduce the size of this, I think. Yeah. Okay. Guys, is this still visible? Can you confirm that this Table is visible? Is the table visible? Okay, perfect. So the dependence over here is basically telling me whether this is the subject or not. So end subject, I believe, is the subject kind of dependency. Root is basically the root word. So a root is essentially the root of this tree, right? So for example, over here, love would be the root of this. So in the tree form. So if you guys want to sort of play around with this, let me just copy this link and share it. Yeah. I'll quickly share this if you want to play around with this dependency parser. So yeah, uh, at the end of the day, we have these kinds of relationships between these words. And now the point is we have to now think about what is the most important verb among all the, what is the most important uh, noun among all the words that we see here, right? At the end of the day, that is the kind of relationship that we're after, okay? So what we have to understand here is two things. First of all, Spacy will automatically give these relationships between these words to us, okay? Second, we will always have a root word. The root word will basically go and expand into a tree, and how these words are related to the root word is what we have to exploit, okay? So based on a very, very naive approach, what we can say is, if we just look for this n subj, right? N subj is basically the subject of your sentence. So the subject of your sentence is the most important noun uh, about which the sentence is, right? So if we look for this n subj kind of relationship, we can only keep the nouns which have this relationship with the root word. And then we can go ahead and see how to do things, right? So let's code this up real quick and see how that works. Okay, cool. So now what we're going to do is we're going to create this graph, and we're simply going to do a very simple thing. We're not going to apply much understanding over here of these labels. We're simply going to take these words. We're going to see what is the root word associated with this noun. Okay, let's just do that one small simple thing and see what we get. Okay, so if I now go ahead and do the following, okay? So in new NC, so new NC is basically this representation for this noun phrases. And then what I'm going to do is I'm going to essentially look for the parent of this current noun, right? I'm going to look at the parent of that noun. So I'm going to take my original word and I'm going to, with an arrow, I'm going to show you what is the parent for that. If I do this for my first 10, this thing, right? If I do this for my first 10, if I do this for all the documents which are there in my data set, and then show you the most common pairs, right? This is what we get. So wherever the word price has appeared, the parent was for in 583 instances in my entire data set. Wherever the root word, wherever the noun was yours, the parent was for 503 documents. So for guitar, it was on, for thing, it was is, and so many occurrences, and so on and so forth, right? So this kind of gives me an idea between a parent-child relationship between my part of speech, which is my noun, and wherever it is coming from. Do you guys think this is really helpful? Do you guys really think this is helpful? Can we get any interpretation from this? I want you guys' honest opinion here. Not really, right? The parent is not good enough. It is not good enough for us to just look at the parent-child relationship. We also have to take these labels into account, right? We have to take these labels into account. So for the sake of this lecture, actually, we're not going to go in that deep, but I encourage you guys to maybe take up the Spacey documentation, sort of see what each of these things mean, and sort of come up with a more heuristic or a better heuristic algorithm which is able to tell you the relationship between these, and maybe that will be more effective for topic modeling. But for the sake of this lecture, we're not going to go into the depths of that. Okay, so instead what we're going to do is we're going to talk about something which is known as topic modeling with statistics. Okay, so now we're going to try and use statistics to build a generator model for this topic modeling. Okay, we're now going to go ahead and discuss how to think about LDA, how it is developed, how to apply it, all those things we're going to take a look. Just quick question. Do you guys want a quick break over here, or Should I start this right away? Okay. So multiple people want a break at this point. Okay. So let's take a quick break over here. Uh, Once we come back from the break, we will go into the depth of LDA. Okay. We're going to go into the depth of LDA. Cool. So I'll see you guys in 5 minutes. Prasad, today's class I will try my best to finish off on time. Like at max, I'll take 10 minutes more. Max. And we're back. Quick confirmation, we're back. Okay. Two people are not back, but still managed to hit the no button. Nice. Okay. Five people are back at least. By my assumption, six people are back. Okay. Awesome. A lot of people are back. All right, guys. Cool. So let's start talking about topic modeling. Okay. Cool. Like I said, whenever we talk about topic modeling, it's kind of important to understand what is a topic, right? So let us first define or try and understand at a very core level what a topic is. A topic, can I at the base level say a topic is a word? Can I say that a topic is a word? Yes, right? Okay. Now that it's a word, is it a word which appears a lot in my documents? Is it are topics words which appear a lot in a document? Yes, most important words in the document, right? So how should I define a topic's importance? Should I look at the frequency? Should I look at how many words are related to this or something like that, right? Rather than the frequency. So the question is this case, sorry, I'll frame it a little better. Should I look at just the frequency or should I look at how many words occur along with this, right? Occur along with this. So strategy one or two, frequency or number of words which are related to this. Yeah. Yes, contextually and semantically. Perfect, Arun. That's a very nice definition. But if I talk about it in terms of numbers, the topic is going to be looking at, we're not just looking for frequent words, we're looking at how many words in this document are built around this word, right? So we need to capture that idea somehow. Okay, cool. So how can we capture this idea? If we take a very, very naive approach, right? I just want to go back to the discussion we were having before this class, before I actually started with the Jupyter notebook, because in our discussion, both aspects came. Okay. So I just want to go through our discussion. So first we said matrix factorization, right? Matrix factorization helps me kind of get what are important words in terms of frequency. Why? Because this bag of words matrix that I have here is recording the frequencies there, right? So intuitively speaking, if I take the bag of words model, where I basically have the frequency of words per document in this matrix, and I get this embedding words, this is going to capture the frequency part of it. But this is not enough. I also want to see how things are related to each other, right? That relationship can be captured through clustering. Okay, that relationship can be captured through clustering. So I'm not only looking for important words in the whole thing, I'm looking at importance in terms of how close it is to other words. Okay, so how do I build a model around this? How do I build a model around this? Okay, let's now talk about statistically speaking, right? How could I think of a way to generate these documents using topics? Okay, so okay, to give you a nice example, if you had to teach a child, okay, a 5-year-old child, how to write a good essay, okay, let's talk about that. The tips that I would give a 5-year-old child is, first, don't start writing the essay directly. Okay, Arun's answer is use ChatGPT. No, Arun, we don't want to teach children to be reliant on tools. We want to teach children to get jobs done if the tool is available or not available. Okay, it's important to teach children to be general. Okay, otherwise what you're saying is overfitting now, right? If ChatGPT doesn't know about something, right? Let us say you took your children on a field trip somewhere, and ChatGPT doesn't know about the field trip. Isn't it overfitting if the child writes about the field trip using ChatGPT? It's overfitting. So we don't want to do that. We want to train a child properly. So if I had to break down the task of essay writing, okay, the tip I would give a child is, first, decide what is the main topic. Okay, the main topic. Then decide what are the subtopics, right? And so on, right? Let us say the child is only expected to write 3 paragraphs, right? 3 paragraphs is what the child is expected to write. So let us say I tell the child, okay, First, think the main topic. The main topic is something the teacher will give you. You don't have freedom thinking about main topic. But once the topic is given to you, think about three things you want to talk about it, right? So that will become my subtopics. Now that I have subtopics, try and form sentence one under this subtopic one. Sentence one. So let us say I'll tell the child, try to write 3 to 4 sentences per subtopic, and that will become a good essay. You will be good at essay writing, right? For a 5-year-old child, that is good enough. Okay. Sentence two, sentence three. Okay. Similarly, now with subtopic two, you have sentence one and sentence two. And finally, with this subtopic, you have sentence one, sentence two, sentence three. Right? Is this intuition okay with everyone? Do you think this is good enough for a 5-year-old child to write an essay with? What do you guys say? Yes or no? Do you agree? This strategy is good? Okay. Now, let us build some math around this strategy. Okay. Whatever I'm going to discuss with you now, the latent Dirichlet analysis allocation is simply going to be a way for me to mathematically capture this idea. To write a document, you first need a topic, you need some subtopics, and then whatever you write is related to the subtopics. Okay. Broadly speaking, this is how I structure a document. Using this very basic understanding of how a document is formed, let us go ahead and see if we can build some math around it. Okay. And the math works out to be very beautiful. Okay. So now let us see how that idea, which I just told you, which was instructions for a 5-year-old child to write essays, let's see how we can capture it in the form of a random process. Okay. So now instead of a child, imagine you're teaching ChatGPT how to write. Okay, no, you don't need to teach that ChatGPT. Let us say you're trying to teach a language model which knows nothing how to write an essay. Okay, something like that. I want you guys to imagine that. Now, let us see what all we can do. Okay, cool. So first of all, the idea, so what is the first task that we did here, guys? The first task which required some amount of thinking was these subtopics, right? Subtopic one, subtopic two, subtopic three. This was the first idea that we had to come across. So now what I'm going to do is I'm going to tell my computer to first identify the subtopics inside the corpus. Okay. I'm going to tell this machine to first identify what are the subtopics. So for this specific example, let us say that the subtopics I have are sports, animals, and tech. Okay. I understand that they're not usually subtopics in a single document. I totally get that. But for now, for the sake of example, let's move with this. Okay, guys? So I have asked my computer to first pick these subtopics. Now, around these subtopics, what am I going to do? I'm going to say for each subtopic, identify the words which are most commonly there, right? Why words? Because I want to write sentences or I want to build a story around these words. So first of all, I have to first see for this topic, what are the important keywords? For the next topic, what are the important keywords? For the final topic, what are the important keywords? That is what I will ask the child to do, right? So then this is step two, okay? So step one is first identifying the main subtopics. Step two is identifying the words which are most related to these subtopics, right? So this is step two. Once step two is done, once I know that, for this topic, these are the important words. For this topic, these are the important words. For this one, these are the important words. I can go and say, randomly start putting these words together to form a sentence. Okay, randomly. I don't want to put any more brain over here. I just want to tell the computer, okay, randomly pick some of these words, build a document out of it. And largely speaking, guys, this is exactly the intuition behind this method, which is known as latent Dirichlet allocation. Okay. So broadly speaking now, whatever we were asking that child to do, we're asking a computer to do. The tools that we're giving the computer is the following. Okay. We're going to give the computer one probability distribution here. Okay. Specifically what distribution? Okay. Arun, I'll come back to you. Guys, do you guys need a repeat of the whole process? I think I went a bit fast. Just hit a yes if you want a repeat of this. I'll repeat this if, okay, cool. let's do this again. Sorry, I'll go a little slow. I'm sorry, I got a bit excited and okay, let's go through this a little bit more slowly. The first thing I'm going to ask my algorithm to do is pick the main topics. Okay, step one. Step two is ask the I'm going to ask the computer to figure out what are the most important words which are associated with this topic. Okay. So at the end of step one and step two, I have for each topic, I'll have a set of words. Okay, cool. Now the question is, using these words, how do I do sentence formation? Right? How do I do sentence formation? Okay. Can you guys tell me if I'm representing everything in bag of words, in the bag of words model, are we able to capture the order in which the words appear in a sentence? Are we able to capture that relationship? No, right? No, we're not. Okay. Huh. So this is what I'm going to tell my computer. I don't care about whether you're able to give me proper sentences or not. I just want you to give me a bag of words essay. Okay. I'm asking my computer to basically say, do the following. With each of these sets, right? With each of these sets, I want you to give me a matrix, a bag of words representation matrix of the document. Okay. I don't actually care if this model is able to form meaningful sentences or not. Why? Because I want to use this model for topic detection, right? So I'm not even going to bother teaching this model how to form sentences. See, if they had figured, so guys, this paper was developed in 2003. Okay. It was developed in UC Berkeley, I believe. I don't remember the authors, but this has been a very popular method for topic modeling since 2003 till 2014-15. Okay. Um, if those guys had already achieved sentence formation, we would not need ChatGPT, right? The task of training a computer model or a probabilistic model to put sentences in the correct order is actually a very difficult task. We were not able to do this till transformer models came and till we used human interference to train those transformer models. Okay. So as far as difficulty of the task goes, it's very difficult to get these words to organize in proper sentences. So what these scientists thought was, okay, I don't care if you're able to give me proper sentences, just give me a bag of words representation. I'll do my training against that. Okay, I will train my model against bag of words. I don't even care if you're forming sentences. Is this part clear now? What is happening after step two? After step two, all we are doing is we're asking this model to give us a bag of words. Whatever training we're going to do of this, we're going to do it with the bag of words representation. We're not going to bother about sentence formation. Okay, cool. Okay, coming back. So now so let me actually restart the discussion. I think I lost track. I'll just give me a second, guys. I need to just recalibrate. I'll in the meantime, I'll just get rid of this. Okay. Okay. All right. Okay. So hopefully now the basic idea behind this latent dirichlet allocation is clear to us. We want to say that a document is or an essay. So think of a document as an essay. Okay. A document is generated as follows. First, a machine figures out what is the main topic. Then the machine figures out what are the subtopics. Then the machine figures out what are the most important words associated with each subtopic. And finally, it is going to create bag of words representations for each document using these important words. Okay. So guys, this is something which is known as a generative stochastic model. Okay. If you go back in history and you look at the last 20 years, right? This method has been the most commonly used method for doing generative modeling. So the idea for GANs actually came from stochastic models which did this. To give you some context, if you know what variational autoencoders are, right, in CNNs. So in CNNs, variational autoencoders are an alternative to GAN. Okay, you can read about it in your spare time. Try and do that, please, because it's kind of an important topic. The main logic behind variational autoencoders comes from this idea, where we first think of a very, very naive algorithm for how to get this job done. Then instead of getting people to do the job, we get these probability distributions to do the heavy lifting. Okay. So let me now elaborate on this idea. Once this basic framework is ready, how do I do the heavy lifting with a probabilistic model? Let's talk about that. Okay. Okay. So what I'm now going to do is I'm going to define something which is known as alpha. Okay. This alpha that I'm defining here is actually a Dirichlet probability distribution. Okay. Does everyone in class remember what Gaussian is? Everyone in class remembers? Can you guys quickly tell me what is the parameters of a Gaussian distribution? What are the main parameters which help me define a Gaussian distribution? Parameters? Mu and sigma. Perfect. Right? Mu and sigma. So just like mu and sigma help you define a Gaussian random variable, this parameter alpha and beta. Okay. So I have one parameter here called alpha. I have another parameter somewhere here called beta. Together, alpha and beta. So not beta. Okay, let's ignore this beta for now. You can think of this alpha as a vector. Okay, you can define something which is known as a Dirichlet probability distribution using this vector called alpha. Let me quickly show you this in Wikipedia. Okay, okay, I'll have to Wikipedia. Latent Dirichlet distribution. Yeah. So yeah. So guys, broadly speaking, this Dirichlet distribution is a multivariate. It's a multivariate distribution. What do I mean by that? Gaussian will give you just one number for each sample, right? What is special about this Dirichlet probability distribution is if you ask for a sample, it will give you a vector or it will give you a matrix, and you can tell this how many things you want, right? When you were studying GMMs, do you guys remember you used multivariate Gaussian distributions when you were studying GMMs? Have you guys studied GMMs? You have, right? Huh. So just like we had multivariate Gaussian distributions there, which gave us one vector. Yeah, D-dimensional Gaussian. It gave us a D-dimensional vector every time we sampled. Just like that, a Dirichlet distribution can give us a matrix now. Okay. So if I ask this distribution for a sample, it will give me back a matrix. So now what I'm going to do is I'm going to put a Dirichlet probability distribution here, and the parameter that I'm going to give this Dirichlet probability distribution is this vector alpha. Okay, it's this vector alpha. What is the job that this alpha is doing? Right? What is the job that this alpha is doing? Let's talk about that. The job of this alpha is to give me a matrix now. Okay, so for the sake of argument, the number of topics that I have here are 3, right? The number of topics that I have here are 3. What I'm going to ask this Dirichlet probability distribution to give me is basically just one moment. I just want to make sure. Yes. So actually, let me do something. Let me actually define all the parameters first, and then we will come back to this. So let me first specify my notation here. From now on, wherever I use the letter K, right? K is nothing but the number of topics. Okay. I have V as my number of size of vocabulary. Vocab size. Let me say M is the number of documents. Then let me say N is the number of words in each document. So guys, notice one thing over here, right? Notice one thing over here. This number of words in each document is I'm basically forcing a model here because I want to do bag of words like training, right? I have to force my model to only generate n words. Okay, so this is one small glitch that you will see. Just keep this in mind. Whenever I ask my model to generate a document, right? I'm forcing it to generate it of size n only. Okay, that part is fixed. So just want you to keep that in mind. Yeah. Yeah, actually, this is all I need to explain this. Yeah, let's use these to understand what's going to happen. Okay. Indradeep's question to me is K a hyperparameter? Yes, Indradeep. In latent Dirichlet allocation rate, K is a hyperparameter. I have the freedom to choose that. Extract 10 topics or extract 5 topics. I have the freedom to choose that. Let us now see how matrix factorization comes here. Okay. Let's see how matrix factorization comes here. Okay. So guys, remember the matrix we started with at the start of the class was basically number of documents, okay, which is M times vocabulary size. You guys remember this? Can I represent my entire corpus as this one hot encoded matrix, which is M cross V? I can, right? Okay. Now, here is the idea, okay? I want to now use some mathematics to capture this simple idea. So what I'm going to do is I'm going to first take this kind of thing, okay, and I'm going to intuitively factorize it into the following. I'm going to get one M cross K. I'm going to get one M cross K thing over here, and I'm going to get another K cross V thing over here. Okay, cool. So now what is the Dirichlet probability distribution's job? The Dirichlet probability distribution's job is now to basically give me a vector which is telling me what are the most important keywords in my what are the most important topics in my corpus, right? If I want the most, so let us now assume K is the number of topics, okay, and M is the number of documents, okay. So per document, from each document, if I want to figure out what is the important topic for that document, can I imagine that that can be encoded in a matrix of size? This will be K, and this will, no. It will be V cross K, right? Yeah. So it will be M cross K. So I'm just, yeah, I'm going to keep this as M, and I'm going to keep this as K, right? Basically this matrix, okay? So now see here, how am I converting this simple idea into math? Let us see. I have this Dirichlet probability distribution. The job of this Dirichlet probability distribution is to generate this matrix for me. This matrix is now going to contain a certain number, okay? Okay, each entry in this is a number, right? So let me call this matrix as my theta matrix, and let me call each entry as theta ij. Okay, theta ij. Is everyone with me so far, guys? This is kind of complicated, so I'm going a bit slow. Just quick check. Is everyone with me? Okay, at least two people are with me. I sincerely hope the others are also there. So let's go ahead and see, right? Okay. Now this theta ij that I have is basically going to tell me for it's going to tell me the probability, okay, it's going to tell me the probability of this topic, this topic, right? The K over here is the number of topics I'm asking it to extract. So what this theta ij is telling me is this topic, right? Is this topic. So let us say theta ij, the J is basically the row number, the I is the column number, right? So is the jth topic over here in this vector? Yeah, exactly. Is this topic important for this doc? Yes, it is going to tell me the probability of topic presence in the particular doc. Perfect, Arun. That is exactly what this matrix is modeling. Okay. So this matrix now is going to model whether this topic, whether this jth topic is important for the ith document over here. Okay. That is what this is going to give me. So this has actually given me the left part of this matrix factorization. That is the interesting thing over here. It has given me the left part of this matrix factorization. So now, don't you think I should do something to get the right part of the matrix factorization? I have to do something to get the right part now, right? Okay. So now let's see how to get the right part. Now, what is the right part intuitively speaking? Intuitively speaking, the right part is telling me for a certain topic, which vocabulary term is important, right? Which word in my vocabulary is related to this topic, right? Don't you think this is what this is capturing? This topic has these words important. Exactly. Okay. And this is what I'm going to do in step 2. Okay, this is what I'm going to do in step 2. So in step 1, I'm going to use a Dirichlet probability distribution to tell me, it's going to give me the distribution of which document has which topic important. The next step is going to give me, for this topic, what words are important. So just like I had Dirichlet probability distribution here, so let me call it Dirichlet 1. Okay, this is the first Dirichlet probability distribution I'm going to use. Same way, for the second step also, I'm going to have a second Dirichlet probability distribution. So let me just abbreviate it. Dirichlet probability distribution. I'm abbreviating it, guys. I hope you will understand this. I will have a second Dirichlet probability distribution, which is going to use a parameter which is known as beta. Okay. So just like I had alpha for this probability distribution, I have beta over here now. The job of this Dirichlet probability distribution is to give me the right-hand side of this matrix. It's to give me that right-hand side. How is it going to do that? It is going to generate a new matrix now. Okay. This is going to generate a new matrix now. The dimensions of these matrix are going to be K cross V. Okay. Let me call this as, what name can I give this? Z. Okay. Let me give this as Z, right? Let me call this matrix as capital Z, and every entry in this matrix Z is small zij. Okay. Every entry in this is small zij. Now each zij over here is telling me what? For this, so remember, I is going to tell me the topic number, J is going to tell me the word number. So Zij over here is how important is the jth word with respect to the topic number I. Okay. So this is what this matrix is going to give me. Okay. Everyone with me so far? We have in steps 1 and 2, we use two different Dirichlet distributions to get two matrices. These matrices have special meaning, and these are what we have. Okay. Now we are going to use these matrices to do something further with that. Okay. Now, what I'm going to do is I'm going to define another distribution. I'm not sure of the type of this distribution. Just one moment. I'll just confirm if it's Dirichlet or not. No. I have to use a joint probability distribution from these two distributions. Okay. So what I'm now going to do is I'm going to take the matrix that I got from this guy. I'm going to take the matrix that I got from step 1. Okay. So step 2 ka matrix, step 1 ka matrix. These two matrices I'm going to take, and I'm going to apply some matrix multiplication like step over there to generate a matrix which has dimensions m cross v, right? It is not exactly matrix multiplication, guys. It is a random sampling of that, but I don't want to get into the math details. So for now, just imagine that it is a matrix multiplication kind of thing that's happening there. Okay, just imagine that. I will explain it a little better once we do a dry run of this. So there it will become clear how this works. But for now, just imagine that we have this new matrix here, and this is our guess for the corpus's bag of words. Okay, corpus's bag of words. This is how we do it. Okay, cool. So now let me elaborate a little bit, through an example. Okay, through an example, I want to show you how this random sampling works to generate this matrix. Okay, for this, we'll have to now start talking about things in terms of balls. So we'll go back to probability theory class, just like we had a bag and we used to draw balls out, right? I'm going to use that analogy to explain how one forward pass of this model works. Okay, cool. So let us now assume, okay, let us now assume that I have n balls over here. Okay, one moment, guys. Before I go there is a question to me in private chat. I just want to clarify that right away because otherwise it will get tough, right? So the question is, so theta ij gives probability of a document under that topic and zij gives probability of a word per topic. Yes, exactly, Indradeep. This is what is happening here. This matrix is giving me which document requires what topic. This matrix is giving me which topic requires which word. And then when I put this together, I will get a bag of words representation, which should be very close to my original data set, right? Okay. So now, guys, if you have understood this viewpoint, right, guys, this is a matrix factorization viewpoint for this latent dirichlet allocation. Now, what we're going to do is we're going to use random sampling to understand actually how this is working. Okay, actually how this is working, it is through random sampling. So I just want to make that a little bit clear. Okay, so let us say I have 3 topics here, right? So if I count the number of balls here in this example, actually, let me do one thing. This is a bit weird for me to explain. I think I'll go to a new slide and I'll explain the other viewpoint here. Okay, I'll just take the same image and I'll explain with that. Okay. So now let us understand from a sampling point of view what's happening. Okay. So we have this Dirichlet probability distribution here, which is giving us alpha. Over here for this example, I have set k equal to 3. Okay. K equal to 3 for this example. I'm basically going to this Dirichlet probability distribution and I'm saying, boss, tell me what is the relative importance of topics in each document. Okay. Then what this Dirichlet said was, okay, let's say document number 1, document number 3, and document number 5 are sports related. Okay. 1, 3, and 5 are sports related. Let's say 2, 4, and 6 are, so 1, 2, 3, okay, 3, I can't repeat, right? So let me do one thing. Let me just keep same numbers. So let us say 1, 2, 3 are sports related. Let us say 4, 5, 6 are tech related. And let us say 7, 8, 9, 10, 11, 12, right? 7 to 12 are animal related. Okay. So whenever this Dirichlet probability distribution gives me probabilities, right? I will basically be able to categorize each document to the most important keyword. Do you guys see this? Do you guys see this? From this matrix, right? If I just go and do argmax on this, if I just go and do argmax on each row, the argmax of that row will tell me which topic it falls under. So that is all I'm doing here. I'm taking the argmax on the row to tell, okay, for this document, this topic, this document, this topic. Once I have this, what I'm going to do is for documents 1, 2, 3, I'm again going to go and for each of these, sorry, not documents, for each of these topic related words, right? I'm going to now have a new matrix, right? So let us see what that matrix was looking like. This was K cross V, right? This was K. These are the topics and this is V, right? Okay. So now out of all of those words, let us say the probability distribution looks like this. Let us say for the word Olympics, we have how much? So let us actually calculate this probability. So this is 1, this is 4, this is 3, this is 5, and this is 1, right? Guys, can you quickly tell me what's the total? 2 plus 5, 7, 8, 9, 10, 14. Is 14 the denominator over here? Is 14 the denominator over here? It is, right? Okay, cool. I just wanted to check. I'm horrible at arithmetic, so just wanted to check. So now what I'm going to have is for the word evil, I'm going to have 1 by 14. For the word Olympics, I'm going to have 4 by 14, right? For the word AI, I'm going to have 3 by 14 and so on, right? So on. So now this is what I'm going to do. So guys, now the main question is from these two matrices, how am I getting my bag of words matrix, right? How am I getting my bag of words matrix using these two matrices? Okay. Guys, do you see some conditional probability going on over here? Do you guys see the conditional probability going on over here? Can I say that these probabilities are probabilities which are conditioned on K being the keyword? Okay. This is probability of a word given that the topic is K. This is the probability of the this is the probability of the topic. Okay, this is so 1 minute, let me just say topic with T. This is probability of topic given that it's document D, right? If you really think about it, what I want over here is probability of word given document. Okay. Can I now split this probability of word given document as probability of word given document comma topic into probability of word given topic upon probability of word given sorry, probability of document, right? I can basically apply Bayes theorem over here, and I can essentially represent this final probability matrix, right? This final probability matrix, I can represent it as some sort of function of these probabilities, right? So actually, when I'm generating this matrix, right? When I'm generating this matrix, what I will do is I will use this kind of a formula to get this probability vector. Okay. I apologize if this is getting very complicated. The only thing is I want you to understand that whatever we saw here happening as matrix factorization steps can be thought of as probability distributions. You can factor those in. Once you have the exact expression, you can finally arrive at a M cross V matrix. This M cross V matrix can be interpreted as a bag of words representation for the corpus. And this is how I generate the output, right? Ajay, it's not very complicated. It is just a combination of all the concepts that we have learned so far. What is complicated here? Tell me. We have understood what matrix factorization is. We have understood what probability theory is. We know what conditional probability is. We know that for conditional probability, we have to apply Bayes theorem somewhere. If we just collect all of these things together, right, this will make sense. If you guys, for any reason, were not able to follow whatever I'm explaining, right, guys, in the detailed notes today, whatever I'm explaining is clearly given. Okay. So this part is probably where you will struggle, which is why I wanted to explain this part with examples. But if you want to go into the depth of the math, right, please follow this notebook. Okay. Please follow this notebook. So, okay. Anyway, coming back. So how do I do topic modeling? How do I do now? How to do topic modeling with this? Right now, how to do topic modeling here? Okay, so guys, can you tell me? I already know the distribution of the actual bag of words. I have this generative algorithm which is giving me guesses for bag of words guesses. Okay, what I want to do is I want to make these should be the same, right? These should not be the same, these should be indistinguishable. Right? These two things, like the guy. So think of this as a GAN. Okay. Think of this as a GAN. In a GAN, we have a generator which is generating something. We have a discriminator which is discriminating these two. Right? So imagine now one source is this bag of words guesses. The other source is this. Other source is the actual data that I have. Now, how did we train in GANs? We basically trained it to make sure that the distributions of both are the same, right? We can achieve the same thing by using a loss function which is known as KL divergence. Have you guys encountered this term before? KL divergence? Anywhere? Okay. Which topic? I just want to know. TSNE, right? Yes. So in TSNE, if you remember, KL divergence is something which is making sure that the distribution of your the distribution of your distances, right? The stochastic neighbors distances should be very close to a T distribution. That is what we did in TSNE, right? Same way, we're going to now apply KL divergence to make sure that whatever generation is happening here, whatever this alpha is, whatever this beta is, we are now going to train this model so that these two are very close to each other. Okay, so that these two are very close to each other, right? These two are very close to each other. So once we are able to do that, right? Once we are able to do this, we finally get the thing called latent Dirichlet allocation. Okay. So latent Dirichlet allocation follows all of these steps to basically generate believable documents. Okay. In the process of generating believable documents, it has now figured out what are the most important topics, right? So now here is the nice thing about this method. Not only are you capturing what are the most frequent things that are appearing in your documents, you're also seeing its relationship with other words. Okay. So this way of defining a topic is very, very effective. Okay. And let us quickly see this in action. Okay. So if you were able to follow through the basic steps, let us see this in action. By the way, guys, these are examples of that distribution. This is an example of the Dirichlet distribution. So in the Dirichlet distribution, if I give the alpha vector as 1.5, 1.5, 1.5, I will get this kind of a distribution. If I give alpha as 5, 5, 5, it will give this kind of a distribution. If I give alpha 1, 2, 2, it will give this. If I give alpha as 2, 4, 8, it will give this, right? So these are examples of different Dirichlet distributions. Okay, cool. Question is, how do we implement this? Again, we don't need to implement it from scratch. We are going to use Jensen's LDA model. Okay. So from Jensen library, we are going to do LDA model and we're going to see this in action. So let's quickly go through the code, see what the results are, and then we will circle back to how effective it is. Okay, cool. So now what I'm going to do is I'm going to create this new thing called tokenized clean reviews by simply tokenizing my data, right? So after I do that, essentially this is going to take care of things like stopword removal of all the punctuation marks. All those pre-processing steps have been implemented in this tokenized clean function, which we defined before. We're simply going to apply that to our entire corpus, and we're going to get these vectors. Once we get these vectors, we create a vocabulary out of it. So we create the vocabulary using this dictionary function from gensem.corpora.dictionary. Okay. So using this dictionary class, we are able to generate this vocabulary. This is an object. Once we do this, we can simply convert all the documents to bag of words using this. So remember, I needed one actual bag of words thing over here. That is what this is doing. The bag of words for the documents in my current corpus, I'm obtaining by running this step. Once I run that step, I'm simply going to run LDA on this bag of words, right? I'm going to set K over here. I'm going to say K, which is the number of topics is 10, and ID to word is equal to vocabulary. So this is basically the object which is going to tell it which number corresponds to which word. Okay, so that is what it is. So this particular run, there were few updates. So sometimes you get these kinds of warnings. It turns out that it kind of converged over here. If it did not converge, it would have thrown an error. So that is why it's just a warning. So we can ignore this safely for now. And once we actually apply this, right, let us see what these topics look like. Okay. So for completeness sake, let me do one thing. I will take this thing over here. Okay. Oh, sorry. 1 minute. Just give me one moment, guys. I want to show you one example of this properly. Okay. So let's take this result. So I'm taking this result, putting it here. Oh, right. Sorry, my bad. I'll take a screenshot of this. Okay. So this is the result of LDA for the first one. Okay, for the first one. And I'm also going to go and I'm going to get that review here. Okay. So let's go up, get that review over here. We had printed it in the very starting, right? Yeah, this one. Okay. And we'll see if this is effective. Okay. So let's analyze this now. So this is the review. This is LDA on it. Okay. Let's reread the review and then let's see the answer that LDA gives and let's see if it is effective. Not much to write about here, but it does exactly what it's supposed to, filters out the pop sounds. Now my recordings are much more crisp. It is one of the lowest prices pop filters on Amazon. So might as well buy it. They honestly work and the same despite their pricing. Okay. So let's go ahead and do this. So what LDA is telling is this is 0.02 times great. It is 0.14 times good. It is 0.012 times sound. So remember, LDA is now going to give us 10 topics per thing. Okay. So, and these are the topics that it's giving us: great, good, sound, strings, quality, price, wood, time, use, well. These are the main topics it has picked up. And the weighting is given like this. Okay. So it is weighted from the greatest to least. So if I now just look at the top 5 words, can I understand something about this? Great, good, sound, strings, right? Great, good, sound, strings. So strings is not appearing over here, but it sort of tells me that whatever this product is, it's kind of great, and you would use it again, right? This is what we sort of get from this LDA output. So to some extent, LDA has done a decent job of extracting the keywords, the topic words from here. Okay, let us go and see some of the other ones. Some of the other ones are guitar, amp, sound, like, one, good, could, get, quality, better. So the 8th one over here, if you notice, tells me that this is not such a great review, right? Quality could get better is what I'm getting from the last 4 words. So the guitar, amp, sound is good, but the quality could have been better, right? This is what I can get from just looking at this. So if you think about it, we have actually achieved the problem that we had set out to solve. We have actually solved the problem we had set out to solve. And LDA does it pretty well. Okay. So just to summarize what all we have seen today, we started off by defining a problem. Yeah, one moment. So Indradeep says the topics are same for all reviews, right? No, Indradeep, they're not, right? Let's go through this. It ideally should not be. Let me just check that. Great, good, sound, strings, quality, price, wood, time, use well. Guitar, amp. No, 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 no. So Indradeep, what is nice about our generative model is every time it generates something, right? It can use a different set of topics here. So the 10 over there, right? The 10 over there specifies how many words I should first pick out as the important words from the document. So a different document may have different important words, right? That is why we had a big matrix over here, right? We actually had the relationship of which document has which important words. So because we're first constructing that big matrix, we have document specific important topics. This is not going to give me important topics just for some documents. So that's how, right? Okay. Coming back. So now we effectively have a technique which is able to go to a document, figure out what's the important topics and give me a nice weightage for what topic is important for that document. And LDA kind of does that. We started out solving this problem with parts of speech. We saw that there were some nice heuristic techniques which were coming there. Of course, it did not give us great results. We figured out why it was not giving great results because we didn't really sort of look at the meanings of these things and make things, right? We just went for some ad hoc way of connecting these words. So maybe if we can go back and improve on this, maybe we can get better results. But instead, we always have LDA, right? Latent direct analysis. We always have this method which can give nice representations. And this is how we solve the topic modeling problem. Cool. Any doubts at this point? I see that there are a couple of questions, so I will take them. But if anyone has any doubts, please ask me right away. I'm also going to be starting the doubt session. I'm kind of done with the content for today, and thank you so much for being an amazing audience. Remember, guys, if you did not follow the math and stuff, right, of LDA, at least try and remember this intuitive picture. What LDA is trying to do is it's taking a topic, breaking it into subtopics, and then breaking it into words. Okay, that intuition I want you to have. If you were not able to follow the math, that's all. Okay. So Indradeep has a question. In the matrix factorization analogy, the K topics were fixed for all topics, right? For all the docs. Uh, K topics were fixed for all the docs. Let me think about this. I've taken that, I have factorized it. Yeah, yes, you're right. For that analogy, yes, you're right that K topics were fixed for all topics because I did a single factorization, but that's not actually how it's happening, right? The matrix analogy comes when we're going in the reverse way. So we're taking one matrix which is K cross V, we're taking one matrix which is M cross K, and we're multiplying them and then getting this, right? So the intuition over there was just to get the idea across that uh, for each topic over here and for each vocabulary set over here, we can connect documents and vocabularies. So that was the idea. But I hope this got clarified when I went and explained this part, right? When you look at it as a random sampling thing. Okay, cool. So that's what. So we have to understand this at different levels, guys, because the math in one shot is kind of complicated. No worries. That's okay. That's okay. No, I was just wondering, did I say the wrong thing? That's all. Just wanted to check. So yeah. Okay, cool. So I'll first answer Ajay's problem. Okay, actually, I can get rid of Anil's question faster. Let me finish that first. Um, Flip it news case study is not yet enabled, but we had intro session on Saturday. Clicking on project link redirects to today's class. Will it be enabled after today's class? Yes, Anil. I believe mostly it will be activated after today's class. If it does not get activated, right, it's a bug and we'll have to fix the bug. So please let me know on Slack if it stops. If it's not working tomorrow also, please let me know. Or if it's not working after class, just let me know. I will get the bug fixed. Ideally, it should take you to the assignment. So yeah, thank you. Now I'll answer Ajay's question. How do you connect the matrix with the Bayesian probabilities? Okay, let's do this, right? Okay. So first of all, let us go back and see what matrices I have, right? I have one matrix here, which is M cross K. For each document, what is the probability of this being the topic word for that? Okay, so let's build that matrix first. So I'll call this matrix theta. Okay, capital theta is this matrix. The dimensions of this matrix is K, which is the num topics. Sorry, K is on the other dimension. This is M, which is documents, num docs. This dimension is K, which is essentially num topics. Okay. And in over here, I have theta ij, right? So theta ij over here can be interpreted as probability that topic K is important. Probability that topic K is important for, sorry, uh, topic will be I, right? I is the row number, which is doc. J. Probability that topic J is important for document M. Okay, cool. So this is theta ij. Let's look at the other matrix. So matrix 2, I'll put in a different color. Matrix 2. Matrix 2 is now going to be this matrix capital Z. The dimensions of this capital Z matrix are, just 1 minute, I'll just go and see what I had written before. This is M cross V. Oh, sorry, no, M cross V is the final thing. This is K cross V. So this will be K cross V. Okay. This is num vocabulary, right? This is capital V, which is vocabulary. And here I have Zij. So I is telling me which topic. Zij can now be interpreted as the probability that word. So now J is the word J is relevant to topic I. Okay. So Ajay, if you're still around, can you just confirm that this is clear now? Okay. So I now have this probability that topic J is important to document M. So this I can write as a conditional probability. So let's write that conditional probability now. I'm basically saying probability of, so given, so I'm already given, so 1 minute. In this case, what am I given? Uh, this is ground truth ka organization, right? So I'm first generating my topic. So what should be the condition? The condition should be the topic given the document. Okay. So I can interpret this as a conditional probability of topic given document. Okay. So someone has given me a document. For this document, how important is this topic? Right? That is what I have to do here. Uh, then this becomes this. Now, this I have to interpret as a conditional probability again. So given a topic, this time I will be given a topic. What is the probability of a word? Right? Okay. So I have now P of T given D. I have P of W given T. The question is, what is P of? So now the question is, I have to somehow apply Bayes theorem over here to figure out how to get P of. Finally, what is it that I want? I want word given topic, right? Because that is the bag of words that I want. Finally, what I want is P of words given topic. I want to write this. Yeah, words given topic is what I want. Not topic, sorry. Word given document. So sorry. It's words given document, right? W given D is what I want. So if T given D, I have W given T. I want W given D, right? Okay. So now I have to apply Bayes theorem over here somehow. Or if not Bayes theorem, I have to apply law of total probabilities. So I have to see now how to do this. Mm, do we make any independence assumptions here? We don't, right? Okay. This is what we want. What we have is over here, W given T. Okay, fine. So if I want W given D, can I say this is, so now I have to see this as a Venn diagram, right? Just give me a second. I need to figure this out. Right? Similarly, P of W given D is P of W intersection D upon P of uh, D, right? Okay. Now the question is, how do I get this joint probability? So if I want to get a joint probability, I can assume a total joint probability and then break it down. So how do I assume a total joint probability? Shin T, right? This is the total joint probability. Once I have a total joint probability, I can break it down into this, right? Yeah. So if I take this and I condition on one of them. So this total joint probability is nothing but probability of W intersection D into probability of T, right? So the joint probability of W intersection D given T into probability of this. So let's see. Right? Yeah. So conditioning gives me this. So it is this times this time into this. Now I have to further condition this now. Okay. So if I break this down, I can express it in terms of the others. So this is probability of W given T comma D into probability of D, right? This is what this is. And now I have to see how to fit the other conditional probabilities here. So now I can represent this as probability of W given T. So topic and documents, I have to now see if I'm conditioning on both, how do I get it? How do I split this apart? Uh, there's something which allows me to do this. Okay. Okay. Okay, Ajay, let's do one thing. I'm pretty sure that these are the steps that I have to follow, but I'm not able to think about this right now. I somehow have to feel I have to figure out how to relate these two terms. Once I'm able to relate these two terms, I can basically start substituting these over here, and I can get access to this. So can I do something smart here? I have to use some sort of conditioning over here uh, to split that up, right? And how do I eliminate that entirely? I take the marginal with respect to that. So it involves taking a marginal somewhere and assuming a joint probability. So if I somehow so now I have to assume an independence condition here, and I have to represent it as a product of those two. So how do I do that? Yeah, so if I assume that probability of word given topic and document does not depend on document but only on topic, then I get this. Okay, got it. Actually got the independence assumption that I'll have to apply here. So the word depends only on topic. So that is the hidden Markov thing that they assume. Okay. So the inherent assumption here uh, in this approach is your word depends only on topic. It does not depend on document, right? If we make this assumption, then it makes our life simpler. So now let me put all of this together. Okay. So I simplified this as this into this, which I further simplified as this. So now this term becomes, so the joint probability becomes probability of W comma D given T into probability of T, which becomes probability of W given T into probability of T into probability of D. Okay. Now in this joint probability, if I divide this by something, right? Yeah. So I have to take this joint probability, I have to divide it by probability of what to make this conditioned on that. So my word given document becomes here. Okay, let's do one thing. I'm sort of convinced that this is the steps that they follow. I just don't know how to go till the final answer. Ajay, let's do one thing. I'm going to go back. I'm going to read the paper, and if you're interested, we can take this offline, right? So the exact set of equations, like I have an intuitive understanding of this. I'm not able to get the exact equations right now, but I'm pretty sure that you can take those two probability values. You can apply some clever conditioning over there and get this answer. So if you just ping me on Slack, I will just get back to you there. Okay. So I will figure this out, give you an answer on Slack. So I'm really sorry. Don't have an exact answer now, but the idea is you can apply these kinds of probability tricks to do this. So that kind of uh, should answer that. I'll give you the exact answer on Slack. Like I'll give you the derivation. So yeah, cool. So I'll mark your question as answered for now. But yeah, it's not as straightforward. So I guess when I was answering your question before, I made it seem like it was straightforward. It's not. Let's sort of figure it out together. apologize for making it sound like it was straightforward before. Cool. Does anyone else have any other doubts? I'll be happy to take any other doubts. If not, we can end today's class, right? Okay. Why is it called latent? Yeah. So whenever you have this, right, latent means hidden. Okay. So uh, these two Dirichlet distributions that are there, right? These two Dirichlet distributions that are there, which is doing everything. Those things are not exactly those things are not exactly how it actually comes, right? So because these are hidden variables, these are variables which there is no way for me to tell you what this alpha actually should be. There is no way for me to tell you what this beta actually should be because there's no physical process associated with it, right? So these are hidden or model variables, and that is why, because we call these hidden variables, the word latent comes from there. So in this probabilistic modeling, whatever random variables we assume, right, those are known as the latent variables. So yeah, it comes from probabilistic modeling theory. So just one moment, I'll see if I can answer Ajay's question by looking at the explanation here, right? Um, so essentially I have alpha, which is here. It gives me this matrix. Then I have this here, which gives me this matrix. Now I have beta here, which gives me this matrix. So overall, I'm bringing all of these. Okay. My bad. I see. I I forgot to condition on one of the variables here. Okay. Okay. I'll answer Ajay's question in Slack. But I think I know what I missed out. There is this dependence on this also. Okay, cool. Yeah. But if anyone has any other doubts, guys, now's the time to ask me. Uh, Otherwise, we can end the class here, right? Okay, guys. So I guess there are no further doubts. Let's end the class here. Next class, we'll be dealing with recurrent neural networks. So finally, we'll be starting with the deep learning side of our discussion. So yeah, kind of excited about that. I'll see you guys in the next class. Good night. Bye.